Beautiful. I'm going to stop sharing the screen momentarily here, so everybody else has the opportunity to share their screen for whoever wants to. So today is oral presentation day with some papers. I intentionally have not read the papers because I wanted to see the presentations first and then read the papers after I see the presentations. So right now we're going to start with a free-for-all, and anybody who wants to go first is welcome to go first in your presentation. I'll remind you of a couple things. You're allowed the opportunity to use whichever visual aids you want to. So you can use visual aids. You are talking to a technical audience, so all of us who are on this call right now, we're technical in nature, and we understand that. So the talks are technical in nature, and you don't have to explain what a voltage is or what a current is, for example. And then the other piece is that you should take as much time as you need to, but I don't think you need more than 3 to 5 minutes to give a discussion. You know, remember the 3 basic rules when you're giving a presentation. Tell us what you're going to tell us, then kind of summarize what you told us. It's just a kind of a good way of, here's how I open, here's what I'm going to talk about, and then here's how I close. So try to focus more on some of those professional parts of a presentation today, even though I know we're doing this from a distance, but let's try to focus a little bit on those kinds of things, and I'll try to jot some notes down from here if I can do that. Okay, so do I have any volunteers for anybody who wants to go first?
Yeah, I don't mind going first. I can go.
All right, Jack, you know how to steal the screen, correct?
Yep. Yeah, just let me know if you can see it, just to be sure of it.
Yep. Right now I see just the blank screen.
Let me just try and get this working. There we go.
Perfect.
You guys can see that, right?
I can. I see a resistor. I see a carbon resistor.
Perfect. Okay, so the topic that I was given was looking at was resistors. I thought it was an interesting topic just because we do a lot of them in class, but we haven't really dug into them properly. So essentially the model for a resistor that people use when they're trying to explain that to maybe a class of individuals would be a rod with a copper wire wrapped around it. So essentially the more turns in the coil, then the higher the resistance. But that's the kind of model for a resistor, but there's 2 different types of resistors that I looked at. The first was a carbon resistor, as you can see here. It uses a carbon mixture, and that's surrounded by an insulator, which is connected to the 2 terminals as shown in a circuit. The advantages of a carbon resistor are that they are very cheap, and they're really, really useful for like small scale circuit analysis, so maybe like in a classroom. They're commonly used for high frequency applications as well. The downfall is the stability, because they're very easily overheated at small values of current. So that is one of the downsides of carbon resistors. So they're not usually used for larger scale circuits. That's kind of where metal film resistors are often used. They are capable of coping with much higher current values, and they're also capable of dissipating large amounts of power. They, as you can see here, they have a thick, usually ceramic insulator which surrounds the metallic film. The metallic film's usually nickel or tin, usually what's used for that. The spiral, as you can see, kind of acts as if you're thinking of the model, acts as the copper wire. It's laser cut into the resistor, and as I say, it essentially performs the role of the spiral. The advantages of a metal film resistor are that due to the precise manufacturing, they tend to be very accurate with low tolerance, so their values are usually pretty accurate. One of the things that really interested me was the color coding. I know that we brushed upon it in class, but essentially when the color code, there's 4, 5, or 6 band color resistors. Usually the first, second, and in some cases the third, if it's a 5 or 6 band resistor, they correspond to the numerical place value. So as you can see in the top one, the 4 band, the 1 is the brown, the 0 is the black, so it would be 10. And then you can see it's a 10k ohm resistor. The third band or the fourth band, depending on which one you're looking at, is the multiplier. So it can range anywhere from powers of 10, so times 10 to the -2 through times 10 to the -7. So it covers a large range of large and small resistances all the way up to millions of ohms. there's some examples that you can see at the side on the model. The tolerance band is the band on the right as we look at it. So it gives the tolerance of the resistor as a percentage. So going from silver, which is a 10% tolerance, up to the violet. The silver is obviously a less accurate resistor. The violet gives a very accurate resistor all the way up to 0.1% of the value. It's not always given on, it's only really given on 6-band resistors, and it's not really common, but the last band you can see on the 6-band ohm is the temperature coefficient. And the unit of that is parts per million. So for me, this was kind of hard to get the units around my head, but I'll try my best to explain it. So essentially it measures the change in value of the resistor per change in temperature. So the standard, it tends to be 25 parts per million, which is the yellow band. So essentially what it means is that it's a change of 25 ohms per million ohms per degrees Celsius. So if you were to think about it, it's a 0.000025% change per degree Celsius. So that's kind of how that band works. The last thing that interested me was the reasons for parallel combinations. We kind of talk about the equivalent resistance, but it made me think, why would we not, if we're looking for a new value, why would we not just find one resistor that represented that value? Why would we need to put things in parallel? So we all know how parallel resistors behave, and they do seem to be used for just combining resistor values, but they do have a purpose, and one of the purposes I found most interesting was to do with power. So if a resistor is dealing with it's got a large amount of current flowing through it and a relatively small resistance, due to the P equals I squared R equation, it'll dissipate a large amount of power. Due to the power energy relationship, that means often it dissipates a lot of heat. So there's a lot of heat energy which can burn the resistor out. So one of the uses of parallel combinations, if you use 2 or more resistors in parallel, because current splits off in a parallel circuit, you'll have the same resistance value that you've used your combination to find, but it splits off amongst all the resistors. So each resistor is dissipating less amounts of power rather than one resistor dissipating large amounts of power, which reduces your chance of the resistor burning out. Same resistance, less dissipation of one resistor means less chance of overheating, is a good way to think about it. I did really enjoy looking at resistors. There was a lot of interesting aspects that are like the series resistors and things like that, but these were the points that I thought were most valuable that I learned about the resistors. But thank you very much for listening.
Awesome. Go ahead and unshare your screen. That was outstanding, Jack. That was a super job. I will tell you that I've never personally run across a 6-band resistor. I've never seen one. I just want to point out a couple of things just for knowledge for the class and for yourself, if it pertains. That's the nonlinearity part of a resistor. So when we use our models in this class, remember, we're using these very nice, everything's linear, everything's beautiful, everything's ideal. And resistors are not ideal. But you can tell by that nonlinearity factor that you discussed, and you did it so eloquently, is there's very, very little difference in the resistance of the resistor over the temperature range that we're typically looking at. But certainly for people who are using resistors in temperature sensitive situations, it is critically important that they consider those factors to see how that resistor is gonna vary in terms of its resistance and how that might pertain to what's going on in a circuit. So you have circuits that have very, very, very high sensitivities. You need to consider that. That is critically important. Very nice job covering the carbon resistor and the metal film resistors. Those metal films, you're going to find those all over the place now. You can still find some of those old carbon resistors, but it had to do with manufacturability and how well they can make them very, very precise, which you, again, did an excellent job of doing that. I would share this about the parallel piece for what it's worth. I want to make sure everybody understands what Jack described as, let's pretend I needed a 10 ohm resistor. Why would I use multiple resistors instead and put them all in parallel to form an equivalent 10 ohm resistor? And that was the situation he described. When I think of parallel resistors, I think of it from a house perspective. And so from the house perspective, What is delivered to the house is a fixed voltage. And when we put our resistors in series versus in parallel, there are very different things that happen. We want to get that fixed voltage across the resistor. If I have a burner on my stove, and in fact, for those of you who have an electric stove, almost every one of you has 4 burners on the top of the stove. I don't want to turn on burner number 1, get really high heat, then turn on burner number 2 because it's in series, and all of a sudden the current goes down and I get less heat out of the burner because the resistance value is the same. I want to turn on another one that is in parallel that gets the same exact voltage and therefore will heat up to the same exact type of temperature that the first one would. So that's a different perspective of parallel resistors. Same voltage across them. Why? Because we generate voltages. We don't generate currents. We generate voltages. And therefore, when I put a resistor in series with that voltage, I get a current, but it's the voltage that is generated. Outstanding job. That was a great presentation. Really appreciated that. Very thorough, very precise. Next up, any other volunteer to go next?
I'll go ahead and go.
Okay, Connor?
Let's-
Isn't that beautiful?
Wait, hold on. Here. There we go. I was gonna try to see if I could do only part of it, but it's not working out too well. Okay, how's that?
That's great. That's good.
Okay, so kind of tying off of what you were talking about a little bit, how you were talking about doing the stove. Well, I kind of took it on my perspective for this part of the project to go ahead and do some research on like the solar power systems, being that's going to be kind of what I'm working with this summer. I figured that this is a good chance to kind of introduce myself to the topic. So basically, as we all know, we've seen solar panels all the way around. But what makes it different from like a solar farm, such as something like this in a residential setting, which is what I'm going to be focusing on, is kind of, it's mainly like the scale of it. Because there's only so much area that you can do for solar panels, and typically they're put on the roof of houses where they're able to reach the most sunlight. And being that's the case, there's typically three kind of systems. So there's going to be like a grid intertied system, where you have this in addition to like your regular electric source coming from like APS or SRP, and doing it this way, it's just you're able to like reduce your electric bill. And if you do end up powering enough, getting enough solar power from it, you're actually able to send some of that energy back into the system, which they could even, like, when I was doing some research, I saw that they would even like put like a credit on your account if this was the case, if you were able to be putting more energy in the system than you are using it yourself. Another example of this is the same kind of thing. It's kind of more of a hybrid system where you still are intertied with the grid, but at this point you also have like a battery storage device, which is able to kind of cover for your nights and like those cloudy days. So this being the case, typically you'll have like a battery that's anywhere from like 36 to 60 kilowatts. And one of the examples that I was seeing that made it pretty substantial in the market is going to be like the Tesla. It's like the power cell or the power block. Yeah. And then there's also a third option of kind of the system you can go about, where it's going to be like you're going completely off grid, where you're relying solely on the solar power that you generate. So throughout a system, the base component and the start of everything is going to be the solar panel itself. So it has many components, including like a sheet of tempered glass, ethanol vinyl acetate. Then you have your solar photovoltaic cells. Then there's a back sheet, an aluminum frame, and then the junction box. So the tempered glass is just going to be that protective layer that goes on the top. The biggest difference between this and like your standard sheet of glass is going to be they put a special coating on here so it's non-reflective. which has a big increase on the efficiency of the solar cells. And the ethanol vinyl acetate, that's kind of a thin film that surrounds the solar voltaic cells and goes on both sides. It's kind of like a secondary level of protection. It makes sure that there's no like dirt or water that kind of is able to get through and affect the cells. And the biggest thing with these is it also helps to deal with the vibration and like the shock that the solar panels can kind of experience. And the back sheet is kind of like that, kind of like the backbone for the whole thing. It's kind of it's for mechanical protection, and then it also helps out with the electrical components, such as like the junction box, because this is what it's going to be mounted on. And surrounding the whole thing is going to be the aluminum frame. This is just going to be a standard nice brace and kind of like an exoskeleton for the solar panel. So for the solar voltaic cells, it's the way these work is it's made out of a semiconductor of silicone. And there's two versions, the monocrystalline and the polycrystalline. And the biggest difference between the two is the monocrystalline. The silicone it's formed into bars, and then it's cut into thin wafers that's placed into these cells. That's how it's formed up. And the polycrystalline is it uses little bits of pieces of it, and typically it's not necessarily as efficient, but you're also able to get it at a lower price point to justify it. So the monocrystalline is going to be your more expensive model, but also you get the efficiency with it. And then the whole point of the solar panel is to be converting sunlight directly into DC electrical energy. So in this case, the solar panels are each going to be serving at the job of a voltage source. So in this case, and then they act and behave the same way when it comes to the circuit. So then just kind of identifying the different components first before we look at the circuit altogether. So that then next in here comes the charge controller. So this is going to be kind of that protector for like the batteries. So this just makes sure that they're not getting too much voltage or too much current to overcharge them, which could actually fry the batteries. And for a battery for your entire home, that's going to be rather expensive. So we're going to be trying to avoid that. Next, you got the solar battery storage. I was making the example of the Tesla power block. There's actually two of them right there. I think each of these is right around 2 kilowatt hours. No, 2 kilowatts. Yeah. And then these are just the storage sources for energy for the nights and cloudy days. And next comes the inverter. So this is going to be put in place to convert the direct current into an alternating current. And if this is the case, because it serves, at least from the example that I was looking at, there's a set of 4 switches that are able to change the direction of the current. So with this being said, like you have 2 switches going on one way and 2 going at the other way. And when 2 of them are open, it sends like a positive voltage into it. And then when the other 2 are open, it's the negative. So this is how you're able to get that sinusoidal shape that is typically kind of associated with alternating current. So you can kind of see on the diagram above, this is kind of the example of what it is. So the semiconductor switches they're put in place instead of doing like a typical mechanical switch. And these are able to turn on and off thousands of times in a second, just doing this way. So you're able to get that shape. And how you see the curve of the line, that's typically associated kind of with like a line of best fit for like the area underneath the set of the bars. So doing it this way is able to give it the shape it needs and be able to produce a current that it most accurately represents the sinusoidal shape. Then from here, this is going to be pretty much the only things in addition to like your typical like power and electrical system for your house. So as you can see on the diagram, on the far left side, you're starting off with a PV array. So that's going to be your solar panels. And these are arranged in a combination of series and parallel that best fits the inverter. So being that they act the same way as voltage sources, putting them in series, you're going to get the summation of them. and then the current is going to be the same throughout both, but when they're in parallel, you're going to have an increase in the same voltage across each path, but you're going to get a higher total current through there. And from here, it goes into the charge controller. This is going to be that kind of protective barrier for the battery bank or the solar storage devices. This kind of where you're just able to store the energy for when you need it, when the solar panel isn't as readily available. And from here, there's two different routes it can go. This is the first time I was kind of looking into this, so I was a little confused. So there's a DC load, and then it also, or it can go into your distribution panel. So the DC load is going to be mainly devices such as like charging like an electric car, something like that, that benefits more from a DC current rather than an AC. And from here, you're just kind of looking at your standard. And so, well, sorry, let me backtrack a little bit. So it either goes to the DC load, or it's going to be going through that inverter that converts it into an AC current. And from here, this is going to be kind of your standard electrical system, because as you know, like all of our homes, they run off of AC current. That's what all the devices are powered off of. Then putting a direct current through there could actually do more harm than good. That's the best of it. So getting that alternating current in there allows everything to function properly as if you were getting it right from the electric company.
Awesome. That was terrific. A lot of good stuff out there. A couple of comments here. It was fantastic. Gosh, that was so good. So thorough, very detailed. I don't know what's going on in this state. I probably should, especially a state like ours with so much sunlight. But in many states, it is required by law. I don't know if you know this, Connor, if you found any of this in your literature. It's required by law that the power company has to buy back any excess energy that you generate. By law, they're required to buy it back from you. So usually we don't have enough. We need more. But you do generate more, and you have nothing. You have no place to store it. You can sell it back to the power company, and they'll reduce that from the bill that you have. And I don't know if they do that in the state of Arizona. Something leads me to believe that we probably don't, because there are so many people who are generating electricity here. It's an interesting thing. I wonder if you can help me understand one part that I personally don't know of, and that is solar panels. So we looked into solar panels for our home, and the company didn't disclose to us. So I did some research and some reading about solar panels and found out that two things. One is basically your energy bank, your bank of that you use to store, and with your inverter. I think it's a combination of the bank, the inverter, and I think it's the voltage regulator as well, which you charge controller. I think that's only good for about 10 years.
Yeah.
And, right? Is that right, for 10 years? And so when they build this plan for you, the plan has you replacing that in 10 years. And then what they never tell you is that the solar cells are only good for 20 years. What causes solar cells to break down? Is it those layers that you described? Well, why? I don't understand why they break down.
So part of it is they're still kind of like a newer concept in reality. Like we're getting to a certain point, but really we're only at like 20, maybe 35% efficiency at the most.
Exactly.
So part of it is like that UV light getting on there. It's over the years, it's causing damage to it. It's not so noticeable, but once you get to that 20-year mark, I think what I was seeing was it's the efficiency that drops so much, so that's why they're wanting it to replace it.
That's right. So do you have any idea? Is there a singular component about it that causes the energy to drop? I mean, if today's technology says that these solar panels are good for, I'm making it up, but it's in the ballpark, 35% conversion, then why can't it convert 35% 10 years from now? There's got to be something that loses its ability to, right? I don't know what it is.
Yeah, I haven't looked into it that much with it, but I'm sure this summer that I'll kind of be able to get a little bit more of a deeper understanding on it.
Terrific.
Just from what I know is just that it's not operating the same way that it used. Is then the same thing kind of goes for like the batteries and the inverters. Just they have a certain lifespan that they're supposed to be switched out on, but I don't necessarily know like what part of it is causing it to fail.
Okay. That's awesome. It's a great presentation. Thoroughly enjoyed that. Well done. Anybody else have questions for either Jack or Connor about their presentations, what they covered that you're interested in? You know, it just came across your mind while you were watching the presentation, want to know what the answer was. We're not trying to grill anybody to embarrass them. It's like, hey, I'm really interested in that. What about such and such? Okay, if not, looking for the next volunteer. Who wants to be our third person this morning?
I'll go ahead and go.
Awesome, Jordan.
Yeah, work okay?
That's beautiful. Yeah, that is terrific.
All right, perfect.
You probably want to do in the PowerPoint, you want to put it in presentation. Yeah, there you go. Okay.
There you go. Okay. All right. So I chose electrical transformers to do my research on, just because I know a little bit about them already, and in my future field, this is probably what I'll be working with a lot. And I know that in class already we've talked about it a lot, so probably a lot of this information is just reiterating, but some of this information can be new to you guys as well. So basically, there's a few types of transformers that you can find out in reality. There's some on like the telephone poles that you see there. They're kind of big, cylinder looking things. And then you can find them also in electrical substations that you see around here and there. Usually they're in the middle of nowhere, but because they're so dangerous. But yeah, I think I see about 4, I think there, or there may be a little bit more, but there's about 4 there. So what are transformers used for? Transformers are basically machines that can transfer electricity from one circuit to another, that change the voltage but doesn't change the frequency. They are also used to change the amount of voltage from one area to another, and they allow you to have a change in voltage in one area compared to the other. So you can have different voltages from one transformer to another, and then they kind of, transfer back and forth to each other, different voltages and the currents even. So how do they work? So transformers work by pushing signals through the coils inside of those cylinders and those boxes. And it changes the magnetic field around it. And it will pass through the secondary one, creating a voltage like we explained in class and all that. And it affects the AC signal from the primary to the secondary transformer. So one type of transformer is the AC transformer, which is basically alternating current. It stands for alternating current. And this is the most common one. Basically passes AC signals to other AC signal transformers. And if you think about it, think of it like a power source being hooked up to like a shaft that is being pushed and pulled through some water. So it's, when it's being pushed, like more water goes through than it is being pulled. And it's just, going back and forth, up and down, or side to side, whatever you have it. And graphically, the signal represents a sinusoid. No matter the length of time, it would always have that alternating current up and down that specific time. So the other type of transformer is the DC transformers, basically, direct current. They have transformers that will pass AC signals to DC signals, or vice versa, whatever you have, but they are less common. And think of it as a hose with water coming out with the spigot turned all the way, and you put your fingers in front of it, adding resistance, but the same amount of water is still going to flow through it no matter what. And then graphically, you can think of it just as a straight line, no matter the length of time involved. And this is your kind of at-home transformer. basically they're called step up or step down transformers. Basically, step up meaning, you know, rise the voltage to a certain amount, and then step down is, you know, lowering the voltage to a certain amount. Basically to kind of create balance with voltages, so you know something doesn't go awire and explode. Just kind of levels things out and makes things more safer, because you know electricity is, as we all know, is kind of dangerous. But yeah, thank you for listening to my presentation.
Excellent. Very good. Again, well described, well defined. I know we haven't covered this in electronics yet, so nobody's quite sure and familiar with this, but the AC to DC transformer still has a part in it that looks just like the AC transformer. It's a matter of, so Gordon talked about you're changing the voltages. That's basically, when we think about transformers, you should always think of what you're doing with a transformer is it's AC on one side, AC on the other side, a voltage on the primary, and I want to get a different voltage on the secondary for whatever reason. So we're either going to step the voltage up, as he said, we're going to increase the voltage, or we're going to step it down, we're going to decrease the voltage. It's one or the other. Usually in an AC to DC transformer, we're stepping the voltage down. And the reason we're stepping it down is because we want a smaller DC voltage. Like you know that a lot of batteries that we operate on, car batteries, are 12-volt batteries. If we look at voltage coming out of the electric socket that we're used to in the house, that peaks at about 185 volts. So we're stepping that down to a different voltage level. And then what we do is we do something. He described a kind of really interesting way to describe kind of what happens when you go AC to DC, but we don't know what these things are. We end up using some filters, which I don't think we're going to have time to talk about filters in this course. I was hoping we would. So we do some filtering, which does some really interesting stuff. And at the same time, we use some diodes, and diodes are nonlinear devices. And what we do with those diodes is we take the lumps of the sinusoid. We know it goes up, it goes down, it goes up, it goes down. And what it does, kind of like a little bit like what Connor was talking about, is it manages to flip them both so that they go up and then up. So we get a lump up, a lump up, a lump up, a lump up. It takes the ones that are negative, flips them to positive, and then it smooths them out. That's what the filter does. It smooths them out, and that's how you end up with DC. So the AC to DC transformer still does AC to AC, but then takes the AC part and converts it to DC. What's really interesting about how this relates to the talk that Connor gave us is we have a handful of things in our house that operate off of DC. Not your oven, not your light bulbs, although some of them could. Your lighting, if you have landscape lighting, is DC lighting. But we have a number of things. And those things that operate on DC electricity, we use transformers. And remember this, even though an AC to AC transformer is a lossless device, once you put the AC to DC part in there, there are losses in there. And that's why if you feel like, for example, this right here from my computer, this is a transformer inside of here. And if you put your hands on it, certainly while your computer is plugged in, you'll feel that it's warm. That heat is lost energy. And so the question of the future is going to be, now that we know all of this stuff, and now that we can generate our own DC through solar cells, should we now convert homes to be DC and not AC? And there are lots of reasons that we could do that, but there are other reasons why we wouldn't want to. So another question would be, should homes turn into the following? There's an AC source to a home and there's a DC source to a home, both of them. Because if we can generate DC power without going through the lossy device of the AC to DC conversion, we could save a lot of money and save a lot of energy. So just some things to think about. Any questions for Jordan? Okay, nice job, Jordan. Really nice, very good on a very important concept. Timely as it happens to be. I don't know if you felt uncomfortable because we're talking about it in class and it felt like you may have been repeating in class, but you
Exactly.
you filled in around the surfaces very nicely. I love the pictures of the transformers and the banks of them that are out there. When people start looking at poles, they'll start to recognize what those things are.
Exactly. Yep.
What we haven't really covered is why we transmit. We step the voltage up, transmit it down the power lines, and then step it down. We talked about it, but we didn't cover that in great detail. Nice job. Okay, we've got 4 more left. Who wants to jump in and be the 4th person to give a presentation today?
I'll go next if you want.
Great, Michelle.
Yes. So the topic I chose was three-way switches. A three-way switch is a common type of light switch that makes it possible to control a ceiling light or other electrical fixture from 2 different locations in the room. The reason I chose this topic was for the reason that I have seen these in my house and I don't have an idea of how these work. So I'll be demonstrating with like circuits, a basic circuit. So this is a basic circuit for a 3-way switch. The gray circle on the circuit represents the light bulb controlled by 2 switches. The reason it's gray is because the light is off. The 2 lines ending near the left side of the circuit goes to a power source, which is like the circuit breaker panel in your house. The green rectangular represents the switches, as you can see in the image. The electricity can flow along the upper wire through the first switch, but the pathway is not connected or is broken at the second switch, which the light remains off. As in the picture, the electricity that flows through the first switch now finds a pathway through the second switch and makes the light turn on. As you can see, the circle turned yellow. Let's say it's a large room and the person who entered turns the light on from the switch on the right of the picture and decides to leave the room near the switch on the left, which flips the switch to the other position. And in that case, makes a break in the circuit again and turns off the light. And that's a little basic understanding of 3-way switches. Thank you.
Outstanding. Very, very nicely done. Michelle, I learned about 3-way switches the same reason you wanted to learn about them. And the reason is because I had a bunch of them in my house and I just started electrical engineering in school and I had no idea that there were differences. Like, well, how the heck does that work? Because if you put the same switch in, it just opens or closes, then both of them would have to be closed and it doesn't work. My God, how does it work? And I had no idea how it worked. So I looked it up to figure it out. And I would encourage you, since you do have that interest, to tell me what 4-way switch is and why you would need a 4-way switch when you have more than 2 switches to run a light in a room. So there, you might have some places in your home when you have 3 switches that run the same light, and it's not the same. And you don't use the same switch everywhere. So what was really beautiful, what Michelle showed, is that you use the same switch on both of those switches. They are both 3-way switches. They are 3 ways. Michelle, can you share your screen again and go back to that first slide?
Yeah, let me pull it up. Can you see it?
Not yet. Perfect. Excellent, thank you. I want everybody to look at this switch. Now, we've looked at switches in our class, and I want to remind you, and if you don't get this, I'll share my screen with you. Our switches, it's a wire that comes into the switch, then we've got the arm of the switch, and then we've got another wire that we want to switch it to. There are only 2 dots in there, one where the switch side is and one on the side that we're going to switch to. Here, there are 3 dots. Michelle beautifully put 3 dots in his diagram, which I loved. That's why it's called a 3-way switch. It only switches 2 different locations. So it's interesting that a 3-way switch is called a 3-way switch, but it only switches 2 different ways. It either switches up or down, either up or down. And no matter which one, so right now in this diagram, he has both of his switches are in the up position, but that upper wire makes that connection. And so this is what's bizarre about a 3-way switch. And when you start wiring houses, you'll learn about this, is that you've got to wire one switch to the other switch. Notice only one switch goes to the light bulb. Only one switch is connected to the light bulb, and in this case, it's the switch on the right-hand side. The switch on the left, which he very clearly articulated, the wire coming in comes from the panel. So that's coming from your breaker panel. And that switch then has two wires that leave it that go to the other switch. They don't go to the light bulb. So lots of people are confused about that. So when you start wiring homes, you have to think carefully about how these switches are connected, because it's not the way you think. Thanks, Marcel, for sharing that. Anybody else have a comment or a question for Marcel? Wonderful job. This great presentations this morning. Okay, 3 left. Looking for the next volunteer.
Hello?
Okay. Rishi, it's going to be you.
Sorry, I didn't know if you could hear me.
Yep.
Share this. Can you see it?
Yep, I can see it.
So I did mine on electric switches, pretty much like Marcel, except I ended up doing them on all 4 types. So switches are literally used to just get the flow of the circuit around. It's in 2 stages. You can either turn it off or turn it on, as we all know. There's 4 basic switches: single pole, double pole, 3-way, or 4-way. And then you can also have multiple switches or dimmer switch. So this is a basic circuit of a switch. This used to be live, I'm not so sure. So on the top, when it's open, it's a open circuit, and then when it's closed, it sends like currents, voltages, everything through the circuit to make it function or turn the light on or anything that we need to do. This is a basic single pole switch. So this can only have one like location from where you can turn it on and off. It's the most common at home. So like when you enter a room, it's only at one position. This is a basic 2-way switch. So that's the one we have in our classroom, as we discussed. It's like when you enter, there's one switch right by the door, and then there's one for the teacher. So you can either turn it off or turn it on, whichever way you would like. This is called a double pole switch. This is a 3-way switch, which Marcel just discussed. So it's pretty much showing you. It has 2 brass screws, a green screw and a darker color screw. Lights can be controlled by 2 different locations. So even, it's pretty much showing you like, there's 3 different poles. So each pole so the pole is controlled, the pole controls the number of circuits it has, and then a throw controls the position of the pole. So you can have 2 different controls for, say you have 2 different poles. This is a 4-way terminal. It has 4 terminals with 2 pairs of translators. So you can, or 2 throws. It's pretty much the same thing. Same function as the other ones. Yeah, so when the switch is open, there's no voltage, no current, nothing like going through it. It's pretty much just 0 all the way around. There could be a different circuit, as we discussed in class. There could be a different circuit with voltages, currents, everything going through, but it wouldn't function properly without a switch being closed. Yeah, that's my presentation about switches.
Awesome. Keep that up so we can discuss this. So the beauty of these switches that she's showing, so just so everybody knows, does everybody see where Arushi has shown the dotted line for those switches? Everybody see that dotted line in that picture on the left-hand side? The dotted line shows that all 4 switches, although they don't touch each other, and although they're not even necessarily in the same circuit and generally are not, they all move simultaneously. You can't take the one in the picture where you see the 1P, that's the first pole. You can't take that one and switch that in the downward direction while the second pole, the third pole, and the fourth pole stay in the upward direction. They all move at the same time. And the reason we need switches like this, as all of you know, there are many times when we want to do something simultaneously. We want that all to happen at exactly the same time. If you take a bank of lights on a field, you want to shut the lights off. You don't want to have to shut them off one at a time. You want to shut them all off. Just shut off all the lights. One switch shuts them all off. That would be an example. There are other times when it's different things. It's not just lights. It's I want to shut this light off, and at the same time, I want the fan to go off. So I hit one switch, and they both go off. So that's what these multiple poles are for. Here's what's interesting compared to Arushi's first switch that she showed, which was it's called a single pole, single throw. And I want to describe to you why the technology is so bad. So I want anybody besides Arushi and besides Misael, I want anybody to look at the switch and tell me how many different positions can this switch be in. Anybody know? How many different positions can that switch be? And everybody's touched switches before. How many different positions can you switch that to?
8.
It looks like it's 8, but it's not. It's only 2. 2 times 4 is 8, and there are 4 poles in there. So you're switching 4 things at the same time, but each of them can only be switched into 2 different positions. And so in this picture that Arushi is showing, those 2 ons are the 2 different positions that you can switch to. Okay? Now this one might have, I don't know because I would have to purchase the switch. It might have a middle position, which it appears that it does because I think I see the word off, and that's pretty unusual that that's there. But it might have middle position. Arushi, I want you to go back to your first switch, your single pole double throw switch. There it is. Look at that switch. That one's easy to see. How many positions are there on that switch? Anybody want to take a stab at that one? Anybody but Arushi or Misael? How many positions can you switch that to?
2.
Excellent. 2 positions. The one when your finger presses the circle, that's one position. When you press the line, that's the other position. There are 2 positions. So you can throw this switch in 2 different directions. However, it is called a single pole. That's what these letters stand for. Single pole, single throw. And the reason it's a single throw has to do with the diagram that's next to the 1P and the 1T. And I want you to look at the arm of the switch that is shown being in the up position. There's only one thing that it can touch. And the thing that it can touch is that little round circle that's on the 1T line. When you open it, it doesn't touch anything. So the throw, usually we think of the throw as the number of positions that the switch can be in, but it's actually the number of different connections that the switch can make. So this single pole, single throw can only connect to one thing. Okay. Any other questions or any questions about these switches? Really nice job, Arushi. Great pictures, help you to see things better. I like some of the top and the bottoms of these switches. But as she said, this is the standard switch. When we think of switches and all the switches we've used in this class, this is what we're talking about. This switch right here. That's the one she's showing. But switches can be more sophisticated than that. Okay, if there are no questions, you can go ahead and unshare your screen. And then either Garrison or Terrence, one of you, or I will randomly select by asking somebody to pick a number that I will write on a sheet of paper. Anybody want to be the next person to go?
I'll go.
Okay, and Terrence?
Okay. So I was under the understanding that it was for tomorrow because I'm actually at work and I'm on my lunch. So I apologize for that. I've had to pick up another job due to everything. But I do have the basic presentation down. So I will not be able to share anything at the moment, which I do apologize for.
Terrence,
Yes.
if you don't have to use any visuals if you don't want to, that's not required. It's okay.
Okay.
All
No
right.
problem. Okay. So I basically just stuck with the switches that you'll find in basic everyday use. They're basically four different types. There's a single pole switch. It's the general purpose switch. Is used to control different things like lights, receptacles. Apologize, and other devices from just a single location. You cannot put this in a location. One of the features of this, it has it's a switch that has an on and off marking. Hello, can you guys still hear me?
Yep, I'm good.
Okay, sorry, I just got a phone call as well. Sorry about that. Okay, and another one is a three-way switch, which everyone's been referring to. This one, they're used in pairs, and you can control lights and other objects from two different locations. These switches, whenever you see them, they usually do not have the on and off markings because both sides do basically the same thing depending on which one is up and which one is down. That's that one. Then they have the double pole switch, which are commonly used in industrial places, and they can be found sometimes in home wiring systems as well. It's kind of like a single pole switch, but this one also has a on and off marking control on it, and you can control a device or other equipment from a single location as well. And another one is the four-way switch, which is used between two three-way switches to provide control for either an outlet or a different light fixture from three or more different locations. If you want to, control from more than three locations, let's say about like 5 locations, you would use 2 three-way switches, one on each side, and 3 four-way switches between each of the 2 three-way switches. And that's my presentation.
Outstanding. Excellent, Terrence. So Terrence has described what I mentioned earlier. I didn't tell you, but he just told us now the secret. So when you have more than 2 switches that operate something, whatever it is, I just want you to think of lights because that's the most common thing that we run into in the everyday world. I go into a room and 5 different light switches control one light because it's a huge room and I want to be able to shut the light off anywhere. The 2 at the end, let's define what the ends are. One end, Ms. Sale helped us with that end. That end comes from the fuse panel or your breaker panel, whatever it is. That's where the power comes from. That goes into a 3-way. The other end, one that goes directly to the light bulb, that's a 3-way. Both of those are 3-ways. Everything you use in between is a 4-way. Now, I want you to think about that for a moment. When I described the home that we purchased when we were in Kansas, and I had 3 light switches, and the damn thing didn't work properly, but when switch number 1 was up and switch number 2 was down, then switch 3, I could switch up or down and the light worked. But when switch 1 was down and 2 was up, then 3 did nothing. You remember all that stuff? You've got to figure out, you have no idea. All you see is a switch on the wall. You have no idea which one's the 3-way, which one's the 4-way until you start pulling them out. And so you've got to figure out which are the 3-way switches, which are the 4-way switches, which one runs to the power panel, which one doesn't. And so you start to use multimeters and devices like that to figure all that out and figure out which 4-ways run to which other 4-ways. It matters. It matters. All of that matters. And so he just did a great description for us of the 4-ways are all in the middle. 4-way, 4-way, 4-way. 3-way at the end coming from the panel. 3-way going to whatever the heck it is you want to control. It's not you ran, I don't know, I guess we just need 2 3-ways and 3 4-ways. Just buy them, we'll put them anywhere. Doesn't work that way. Very precise way that they work. And therefore, the wiring in the wall matters. Now, a lot of you are thinking, do we really need to know this? One day you never know. You might need to know it. I did some wiring in my house. I needed to know it. You never know when you're going to stumble into that. So, great topic. Lastly, Terrence, you talked about that you generally see these double pole switches in industry. That's correct. You very rarely do you see them in a home. But if you did, it is probably pretty likely that it's going to be a double pole single throw. A double pole single throw. I turn 2 things on at the same time, or I turn them off at the same time. Versus I switch them from one location or I switch them to another location. That would be the double pole double throw that Arushi showed us. So that, you see that in a home setting, would probably be a double pole single throw. Very rare to find those switches. They're not easy to find. Great, 3 of them on switches. I think that's cool. I understand why. We all know what switches are. We're pretty comfortable with them, and we're probably interested in that topic. So that's great. That was awesome. Real nice. Last one for the day. So Garrison, last presentation. If you're speaking, you're on mute right now. Or you're away from your computer or phone, whatever you're using, and you just signed in with us. Last opportunity to do your presentation. Okay, so why don't we take a break? Let's come back in 5 minutes, and then we'll finish on Jordan's topic today, the transformer, by looking at a couple of circuit examples, okay? So 5 minutes, meet you back here. There we go. We're live, and now we're going to recap. So we're going to do a recap of the material that we had yesterday with regard to transformers. And so a transformer, we know we're going to draw a transformer like the following. And we can use fewer curls if we want to. If it's an ideal transformer, we get that in the middle, and that's going to indicate it's an ideal transformer to us. And then there's a dotted system somewhere. And we'll talk about the dots and how we utilize those dots. So there's our transformer. One side's the primary, one's the secondary. So let's label a voltage on the primary side. Let's label a voltage on the secondary side. Let's show a current. Right now, a current coming out of the out of the secondary into the primary. This is sort of standard. It's not fixed. It's not fixed, but a lot of people tend to draw it this way. Current I1 goes into the primary. Current I2 comes out of the secondary. And then this is what we developed. This is the important part. The ratio V2 over V1 is equal to A. That's unbelievable. Where A, as a reminder, is the ratio of the turns, N2 over N1. So what I like to remember is the voltages satisfy the ratio of the turns. 2 over 1, 2 over 1, they're both equal to A. The current is the opposite. So I could write it this way. We didn't, but it's I1 over I2 is equal to A. But we like to write it keeping the 2 in the numerator, the 1 in the denominator, and when we do that, that's equal to 1 over A. So that's important equation number 1. The voltages, the ratio of the voltages are A. We said afterwards, oh, don't forget, it depends on how the dot notation is. So we want the same thing on both of these, plus or minus. But the last one we looked at was the impedance seen looking in here. This impedance, we call that ZAB. ZAB is equal to 1 over A squared, and then if we put a load over here, Z sub L, it's 1 over A squared times Z sub L. How come I don't put a plus or minus sign on this one? How come I don't put a plus or minus sign on this one? I didn't do a proof to this. It's real easy. But why is there no plus or minus sign? I have plus or minus signs on the other ones. Why no plus or minus sign there?
Because when A is squared, it negates the negative.
That is correct. When A is squared, gets rid of the negative, turns into a positive. Okay, so let's start with an example. Try to get 2 examples done today. And so in this example, I want the following circle. We're going to have obviously a transformer in the circuit, 3 ohm resistor, and an inductor here. This is an inductor, it's not a transformer. Let's label the voltage V sub A across this inductor. It is a 2/3 Henry inductor. And then I have another inductor here, and this one's going to be 1/3 Henry. And then I have my ideal transformer. Okay, and so we'll label this V1 for the primary. In general, these are not labeled. I'm putting it in right now. In general, they're not labeled. You have to identify the primary and the secondary. You get to choose which side is the primary side and which side is the secondary side. Remember, we can put these in, quote, backwards, and it's the same thing. It's just 2 different coils. That's all. So what differs is what the number of turns are on the primary side and what the number of turns are on the secondary side. All right, so an 8 ohm resistor, this is what I'm after, V sub B. So we can solve for anything, but in particular, I want to solve this circuit for VA and VB. This is 10 cosine of 3t. So solve for the steady state solution. Often we get to the point where we start dropping the terminology of the steady state solution, and we just know, go to sinusoidal steady state solution for VA and VB. So that's what we want to do. What do you think step 1 is? Hold on. Let me get the rest of my circuit drawn. Dot here, dot here. So put the same dots here. And then on top of that, I'm going to do this. 1 to 2. And just date my notes here. So I have a date on this. Today is the 9th, 4/9/2020. Nobody's asked the question, but all of the videos are out there. I try to get them out there the same day. All the videos are on the YouTube channel. The links for all of the videos are in Blackboard. So if you go to my course in Blackboard, all the links are there, and all of the notes you can access in Blackboard. Everything's saved there. So try to make it easy for you to access. Okay, so we're solving for this, the steady state voltage for VA and VB. Anybody tell me step number 1?
Does it convert to the frequency domain?
That is correct, Jack. We convert to the frequency domain. I'm going to label a V1 and a V2. Just remember, in general, these are not labeled for you. You would have to put them in there. You define the primary. You define the secondary. All right, so I'm going to convert right here in this circuit. 10, 3 is 3. This is 2/3, I said, not 2/2. 2/3. So we know omega is 3. So up here, let me make that notation. Omega is equal to 3. So if I have a 2/3 Henry inductor, I know J omega L is going to give me J2. Let's put that in a box so we see that. Up here for the 1/3, that's going to give me a J1 or just a J up here. And then minus J over omega C for the 1/12 is going to give me minus 4J. All the resistors stay the same. And what do we do with the inductance of the transformers? It's kind of like a trick question. What do we do with the inductance of the transformers? It's the best answer in the world.
Nothing.
Nothing, because it's an ideal transformer, and ideal transformers are independent of their inductance value. They are independent of the radian frequency. That is unbelievable. We don't even care. All right, let's convert this to V2. There's a VB over there. Here's a V1 here. There's a VA here. Everything's converted. We can find everything that we want to. Now, we can tackle this in a variety of different ways. So one way to tackle it would be to do our work on the circuit that is the left-hand part of the circuit. Just like this part right over here. We can do all of our work there. And then once we do that work, we can find V1 and we can come over here and do that. Here's what I'm going to do. I am going to use the following equation, that ZAB is equal to 1 over A squared times Z sub L. And what I'm going to do is I'm going to take, this is my Z sub L right here. Everybody see that? That's Z sub L. That's the load that is attached to the secondary. And so what I'm going to do is I'm going to replace everything that you see in this box, not a box, everything there. I'm going to replace all of that with ZAB. So I'm going to redraw the circuit with ZAB in place, but I'll still need this circuit up above. So can anybody tell me what A is equal to? Hint, the answer to that question is right here.
A 1/2.
Say that again.
Is it 1/2?
Okay, watch this. And 2
Yeah,
over
2.
1. Yeah, that's correct. That's 2. So this is 1 over 2 squared times Z sub L. Z sub L is 8 minus 4J. Treat all of this right there as Z sub L. That's your impedance. Okay? So let's see what that's equal to. 1/4 times 8 minus 4J. Oh, I was so nice to design this circuit. That is going to be equal to 2 minus J. Not bad. So now we're going to take the rest of the circuit. Gosh darn you. I'm going to leave it all there. Let me redraw it down here for you so you can see it. I don't know if it necessarily helps, but it helps me. So this is J2. This is 10. This is 3. This is J. This over here, from here to here, that's A to B right there. And I'm just going to put it in a box. There are a variety of ways I could do this. 2 minus J. If I were drawing that impedance as 2 elements, I'm sure you know, that would be a 2 ohm resistor and a minus J for the impedance of a capacitor, correct? It's going to be a capacitor because we have a negative J term there. Okay, let's see. What else is here? Is V1 in here? It is. This is V1 right here, if you care. That's V sub A right there. So we can solve for V1, we can solve for V sub A, and we can do that in a variety of different ways. So how might you tackle solving this circuit? Do I need V1? Do I need VA? The answer is I definitely need VA. I'm not sure if I need V1, but I definitely need VA. So we have a couple of choices. We can combine impedances, we can do a lot of different things, or we can just go directly to nodal analysis. I'm going to do nodal analysis because we haven't done a lot of nodes or meshes with impedances. We've been doing a lot of combining and combining and combining, and that's great, but I want to make sure we get enough of a sample of doing it in a variety of different ways. So this is going to be voltage V sub A. So at V sub A, I have VA minus 10, that's 10 right there. VA minus 10 over 3 plus VA over J2 plus VA over j plus 2 minus j. No way. Equals 0. Cancel, cancel. Thank you again. That was very nice. This j here, I can write as a minus j in the numerator. So that'll get rid of it there. And now what's my common denominator? It looks like it's going to be 6. So when I multiply by 6, I'm going to have 2 times VA minus 10 plus a minus 3j times VA, and then plus 3 times VA, and that's equal to 0. What are my VA terms? 2 and 3 is 5. 5 minus 3j VA is equal to 20. Now we can solve for VA. Let's do that. VA equals 20 divided by 5 minus 3j times 5 plus 3j over 5 plus 3j equals denominator 25 plus 9, numerator still have a 20 there, and it's 20 times 5 minus 3j, which is equal to 20 over 34 times 5 minus 3j. I can reduce the fraction out in front because that's divisible by 2. That'll give us 10/17, 5 minus 3j. Now we're asked for VA in the time domain, right? There's the VA. Where's the VA in the time domain? So right now, even though this is a good form for future work that I'm going to do, is it a good form to find VA? Little VA. Is it a good form to find little VA?
No.
What form do I want?
Rectangular form? Or, I'm sorry,
This-
polar form?
Correct, polar form. It's good. 10/17 times what we've already done the 5 squared and the 3 squared, and we know that that was 34. So it's the square root of 34 at an angle tan inverse of -3 over 5. So therefore, not equals, therefore, little VA is equal to 10/17 times root 34 cosine of 3t, oops, we'll close it up yet, plus tan inverse of -3 divided by 5. And that's in volts. So there's one of the answers. Okay, that's the time domain. I still want to work here, though. I still need this because I want, look what we're after. We're after VB. V is over here. In order to find VB, I need to find V2. Once I have V2, I can use a voltage divider. I can't find V2 unless I have V1. But that V1 is this V1 right here. So V1 is still a voltage divider. I'll write it up here so you can see it while the circuit is still there. V1 equals 2 minus j divided by 2 minus j plus j all times VA. Okay, everybody see that? So that I'll rewrite down here. So V1 was equal to 2 minus j over 2 minus j plus j all times VA, which is equal to 2 minus j divided by 2 times VA, but VA is right here. 10/17, 5 minus 3j. So 10/17 gives me 5/17. This is equal to 10/17 divided by this 2, 5/17. And now, times what? 2 times 5, 10 minus 3, 10 minus 3, 7. And then the imaginary part is Did I show my arrows correctly? I guess I just crossed them over. The imaginary part, 2 times minus 3j, minus 6j, and then minus j times 5, minus 5 more j, that's minus 11j. So if I did this correctly, that is equal to 7 minus 11j. That's what I said. Did I do that all correctly? Everything look good there? Ten minus 3, I think it all looks good. Okay. Good. Numbers look okay. Just double checking my numbers here. 2 minus j over 2 times v sub a, and v sub a was 5 minus 3j. Okay, good. Great. So 5/17, 7 minus 11j. That is v1. What's v2 equal to? V2 is not even in this picture. V2 is here. What's V2 equal to? Any thoughts on V2?
V1 times A.
Yes, and A is equal to 2. So it's plus or minus A, and I haven't told you how to pick the correct answer yet, but it'll be plus here. So V2 is equal to 2 times V1. A, V1, it is a positive. And we'll give you the notation to use. Okay, so we have V1. So pop that back in there. Now that's equal to 10/17 times 7 minus 11j. Okay, that's V2. Now we want what is VB? Right over here, what is VB? So VB is over here, and that's another voltage divider. It's 8 divided by 8 minus 4j times V2. VB equals 8 divided by 8 minus 4j times V2 equals, divide by 4, 2 minus 4j times 10/17 times 7 minus 11j. I know numbers can get ugly. Don't worry about ugly numbers. I'm going to multiply by 2 plus 4j. Is that right? 2? That's not 2 plus 4j. Yep. Divide by 4. Let's like 2 minus j. 2 minus j. I don't know where 2 plus 4j came from. So it's going to be times 2 plus j over 2 plus j. And that is going to be equal to what? 20/17. That takes care of all of that. And then what I'm left with in the denominator from this times this is 2 squared plus 1 squared. That's times 5 on the denominator. And now in the numerator, I have this times this. So 7 times 2 is 14 plus 11. 14 plus 11, 25. And then the minus part is 7 plus j minus 22. So 7j, 7 times j, 7j minus 22j. 7 minus 22, negative 15. Okay. Well, 5 divides that nicely. That's equal to 20/17 times 5 minus 3j. That's amazing. Amazing. Okay, not the form we wanted in. Let's get it in the right form. 20/17 square root of remind me what that number was, 25, 30, 34, square root of 34, at an angle tan inverse of -3/5, which will allow VB equals 20√34/17 cosine of 3t plus tan inverse 3t plus tan inverse -3/5 volts. So this is an example of having a transformer in a circuit. And what we do with that transformer is we just reflect the impedance back to the primary side and just put in the impedance and then solve the circuit that way. And that's about half of the time you're going to do something like that, or more than half of the time, more than half of the time, 3/4 of the time you'll do something like that. Other times you'll do something like what I will do in the second example. Any questions on that particular example? So let's talk about this dot convention so we get it right. There are many authors of many textbooks, and they write the dot convention for transformers in a variety of different ways. I actually love what our authors did here. So this is for ideal transformers. So we're going to follow this format for voltages. If the dot is at the same polarity marking for both V1 and V2, so if they're the same. So up here in this circuit, the dot is on the positive side. The dot is on the positive side. Often you can make that happen. So if it's on the same side, it could have been the dot was on the negative and the dot was on the negative. We'd have the same exact thing. So it wouldn't matter as long as they're on the same side, right? They're on the same polarity marking. So if that's the case for V1 and V2, then we use the plus sign in the relationship. Otherwise, use the negative sign. So you, when voltages have not been labeled for you, you can decide to put voltages in it. Even if voltages have been labeled for you, you can put in your own voltages. Just call them something different. And you can put those voltages in so that they satisfy this description, that the dots are at the same polarity marking. They're either both at the plus or they're both at the minus. Okay? For the currents, it's kind of the opposite. Currents. So if the currents I1 and I2 are both directed in or out of the dotted terminals, if the currents I1 and I2 are both directed in or both directed out of the dotted terminal, then use the negative sign. Use the negative sign in the I1, I2 relationship. So we can do the same thing. If the currents are both directed in or both directed out, watch this one up here. So I didn't show you an I2, but I2. I didn't show you an I1. I1, this is pretty typical of what you'll see. I1 goes into the dotted, I2 comes out of the dotted. So they don't go into the same, right? Here's use the negative sign. Otherwise, use the positive sign. In this particular circuit, given I1 and I2, we would have used a positive sign. And so what you'll see is you'll see a lot of transformers that look like the following. Dots are on the top almost all the time. Ideal transformer. Here's your ratio, whatever it is, 1 to A. That's why a lot of people use the 1 to A notation, because the second number, if the first number is 1, the second number is always A. And then they show this, plus minus V1, plus minus V2, I1, and I2. And what we know is when we have this configuration right here, we know the following. V1 phasor equals A, V2 phasor, and I'm sorry, I have my A on the wrong side, apologize. And I1 phasor is equal to, this is where the A goes on this side, I2 phasor. And notice they're both positive. So a lot of people like positives, and here they're both positive, and that's why this notation. There's the dot, there's the dot. This current is in, this current is out. Dot matches up with the plus, dot matches up with the plus. Most people don't even put both dots at the minuses. They just don't do that. Most people put the dots at the pluses. It's just easier to understand. If you stick with that notation all the time, it's always the same thing. Okay, let's do one other circuit today and be done. So let's look at one other example. And this one is going to take a different approach. We're not going to do the impedance approach. So in the last one, we used the impedance relationship. Here, we're going to use the current and voltage relationships. So it's going to look like this. So this will be 244 sine of 22. Here, across here, I have 1/10 Henry inductor, and down here, I have my ideal transformer. And this is an unusual use for a transformer, but if you look at some of the cool problems that are in the book, you'll see some really interesting uses for transformers and how you can put them into circuits and make some other interesting relationships between, besides the V2 over V1 equals A relationship. All right, let's let this be 1/2. Let's put the dot notation the following way. Dot notation here and here, plus, minus. I'll put in the V2 for you. Actually, yeah, let me put it in for you now. I'll put it in at some point in time. We might as well put it in now. And let's make sure we know that this is an ideal transformer. So those bars in between show the idealness of the transformer. Over here, we have a capacitor. And that capacitor is a 1/60th farad capacitor. And then going across, we have a 4 ohm resistor over here. We're just going to connect that at the bottom so that they have the same reference point. Okay, so here's what we want to do. We want to find the current in this circuit. I want to find this current right here. Find I in the steady state. Okay, I know you know all of the gimmicks already. Now watch this. This is going to be the first time I think I've done this with you. I think we may have done this before. I am going to choose a sign reference. And because it is unusual to do that, I'm going to write that down here to remind me and to remind the person who is grading my work. I'm choosing a sign reference. So if I choose a sign reference, it means I take the sign out and then I put the sign back in at the end. Otherwise, everything we do is the same. So we don't carry around the sign, we don't carry around the 20t, we would carry around the phase angle and the magnitude. So I'm choosing a sign reference. So it's 244. Omega is clearly equal to 20. So this is going to give us J2 right there. Let's put that on a box so you see that. That's J2. And then I have the impedance of the capacitor. And if we used omega is equal to 20, I get 20 times 1 over 60. That's going to be 1/3. And I'll flip that. It's going to be a minus J3 over here. This is going to be V2 phasor. This is going to be V1 phasor. This is going to be I phasor. And we might need some other things depending upon what work we do. In fact, we are going to need some other things. I know we will. We'll need I1 and I2. So I'm going to label I1 this way. That's I1. And I'm going to label I2 this way, right here. I2, and you'll see why we want to do that. Okay, now this is going to be bizarre, but we are going to do an analysis on this circuit and see the mesh or nodes, and mesh is not going to be a good choice. Nodal analysis is going to be a good choice. Mesh can be a very good choice in a lot of different situations, but it's not here. So I'm going to make this my reference down here. If that's my reference, then this is a supernode over here, and this voltage is 244. And then this is going to be a node, and this, which is all of this, don't forget it's all of that. That's a node. Everybody see how that node voltage is V2? Everybody agree with that, that that's V2? Okay, somebody help me before we move forward. I want to write the transformer relationships. Using the dot notation we just had, what are the relationships? Somebody help me with V1 and V2. I'll help. V2 is equal to 2V1. All right, now, is it plus or minus?
Minus.
Excellent. Minus it is. Dot on the plus, dot on the minus. They're not on the same, so it's a minus. Okay, now the relationship for I. I2 is 1 over A I1. Question is that plus or minus?
Plus.
Correct. Plus. That is a plus. So we have our relationship for V2. We have our relationship for I2. And now what we can do is we can start to write our equations. So here we go. At V1. So far, the only thing that's different is we put this node here in the middle of two elements. But remember, the reason we have to do it is because we don't have this as an inductor to be able to write something with regard to the inductor. We don't have that, so we need to put that node voltage there. Okay, so at V1 minus 244 divided by J2 plus I1 equals 0. I can multiply by J2 or multiply by 2. It doesn't matter. I'll multiply by J2 for this one. So when I multiply by J2, I have V1 minus 244 plus 2J by 1 equals 0, or V1 plus 2JI1 equals 244. So there's one of our equations. Okay, let's do the same thing at V2. So what do I have? For V2, I have this current going this way. So it's V2 minus 244 over 4. V2 minus 244 over 4. Now, right now, we could substitute in right now if we want to, but let's wait. Let's put those in afterwards. Then I have, whoop, then I have plus I2. Come on. Plus that current right there, plus I2. Plus V2 minus 0 divided by minus J3. Okay, with this one, I'm going to multiply by 12. And I'm going to take this minus J and I'm going to put it up here and I'm going to make that a J. Multiply by 12, that gives me 3 times V2 minus 244 plus 12 I2 plus 4J V2. And I didn't even finish my equation. Nobody butchered me on that one. Thank you for not killing me. Equals 0. All right, let's group the V2 terms. 3 plus J4, V2, plus 12, I2, equals 3 times 244. Now I'm going to substitute in. V2 is minus 2V1. 3 plus J4 times minus 2 times V1 plus 12 times I2, and I2 is 1 over A. I didn't even put in my A value, equals 1/2 by 1. There it is, 1/2 I1 equals 3 times 244. So let's see. I can divide by a 2. This will give me 3 minus 3 plus J4, V1. This is 6. I divided by 2 is plus 3 I1 equals, divide by 2, 3 times 122. Second equation. So we can solve. What would we solve for? Remember what we're solving for in this problem. What are we solving for in this problem? We want I phasor. So let's recall I phasor. I phasor equals V2 divided by, what was that, minus J3 or minus J2? Minus J3. Minus J3. So we need to solve for V1 because V1 is related to V2. So solve the two equations for V1. Okay? 2. V2 equals minus 2 V1. 3. I equals V2 divided by minus J3. 4. Convert back to the time domain. With the following. let's just say this is I sub m at an angle of theta I. So therefore, I equals I sub m sine, shows the sine reference, okay, so don't forget that right here, sine reference. So the sine goes back in, not the cosine. Sine of 20t, oops, there's an angle, plus theta I, amps, done. Okay? And if you do all of that, this is what I scratched out working this problem out. It looks like it's 8 root 122 sine of 20t plus tan inverse of -1 over -11. That's what I got. So check that, see if you get that same answer, if you want to go through the numbers. What I really wanted to show you is how you deal with this when it's in a circuit, and we can't just take this and transform this back to the other side. We've got to be really careful when we do that, because this part up here is still part of the impedance seen by the secondary. Okay, any questions on that? Questions on that? Okay, so you have your homework. Your homework is due on Monday. We'll have one more presentation done on Monday, and then we'll start on Monday on a whole new concept looking at circuits that extend beyond the sinusoidal input world. And we're going to start to talk about Laplace transforms. We'll start Laplace transforms with 3 important functions. We've seen the unit step function. We're going to revisit that one, the ramp function, the impulse function, and then we'll go into Laplace properties and the transform and the definition of the transform. Everybody have a great Easter weekend. Stay safe this long weekend. Be smart. Don't do stupid things, but do one thing that's not stupid. Do your homework, okay? Please do your homework. I will see you next week on Monday.
Dr. Tyner, just before you go,
Go ahead, Jack.
could you send me that in? I spoke to Connor about joining that class meeting that you're having in like the next hour. So can you send me the Zoom invite for that?
Would you like to come to that meeting?
Yes, it's not too bad. It's not 10 o'clock get here, so.
I will do that. I'll send that to you, okay?
Okay, appreciate it. Thank you.
Thanks so much. All right, the rest of you take care. Have a great weekend. We'll talk to you next week.